Good morning, dear students. In this video, we will look into the effect of performing consecutive operations in a chemical group, symmetry elements of a chemical group. Now, we have already seen in the previous videos that there are different types of symmetry elements in a molecule, namely axis of rotation, center of inversion, planes of symmetry, improper axis of rotation, etc. Now, in this video, we will see what is the effect of performing the same operations in consecutive manner. Now, first we will take the symmetry element, the plane of symmetry. The plane of symmetry's operation is reflection. See, you consider this as a molecule, and if there is a plane that reflects this molecule, it duplicates. So, a plane of symmetry does reflection. So, when you are going to do the reflection once, when you are going to perform the plane of symmetry operation once, you get the operation as sigma. But when you are going to perform it once again, you get it as identity. So, from this you understand that the effect of performing the plane of symmetry odd number of times is sigma and even number of times is identity. The similar is the case of your next symmetry element, that is the center of inversion. So, already we have seen what is the center of inversion. Center of inversion is a point in which there is just, you can see, on performing this center of inversion operation, the Cl 1 becomes 4 and 4 becomes 1. Similarly, 2 becomes 3 and 3 becomes 2. So, there is a diagonal exchange of the atoms. This is what is happening by the operation inversion. So, this operation, what happens on consecutive performance? So, when you are performing this operation in odd number of times, you get I as the operation, and when you are going to perform this operation in even number of times, you are going to get E as the result. You are going to get the identity. So, that is what is marked here. In this plate, there is a mistake. Please don't note it down and kindly correct it, and this has to be I. Okay, so this is what we have to understand while doing the repeated operations. Now we will come to the axis of rotation. In this axis of rotation, first of all, let us consider the case of C3 axis of rotation. The C3 axis of rotation generates three particular operations, that is rotating through 120 degree, that is called as C3-1. When you are rotating through the C3 axis once, what happens? This 3 comes here, 1 comes here and 2 comes here. So, this is your new molecule, appearance after performing C3-1. So, once again when you are going to rotate it 120 degree, so you are performing C3-2, that is you are rotating around the C3 axis for the second time. So, this is called as C3-2. So, you are getting a new appearance which is different from that of these two. Once again when you are performing a C3, once again rotation through 120 degree takes place and you are getting the molecule which you took already, that is identity. So, C3-3 is identity. So, on seeing this example, we can understand that you are able to generate 3 operations out of a C3 rotational axis. Those operations are C3-1, C3-2 and E. So, this is the case of any axis for that matter. We will take one more example and let us take it as a reflection spot in which you can try to identify the operations generated by the C4 axis. You can work it out in the book and then you can refer it with this plate. Yeah. after you have done, just look into this. Now, this is the square planar molecule in which all the fluorines, HCF4, in which the fluorines are labeled as 1, 2, 3 and 4. Now, when I am performing the C4-1, all the fluorines are exchanged through 90 degree and you get a new orientation like this. When I am performing another time C4-2, I get this appearance, and I can call this C4-2 as C2-1 because this molecule, when rotated through 180 degree, you can directly get this molecule. So it is called as C2-1. And this particular appearance on further rotation through the axis C4, once again through 90 degree gives this, and once again on rotation through 90 degree I get back my identity. So C4-4 is identity. So on the whole, my C4 axis is able to generate 4 operations, namely C4-1, C4-2, which is equal to C2-1, and C4-3 and identity. So you can get some generalization that a Cn axis is able to generate n particular symmetry operations, and those operations are Cn1, Cn2, etc. up to Cn n-m, and then finally you get identity. So the C4 axis generates all these symmetry operations. So this is what is the general rule. This general rule holds good when n is even or odd in the case of your proper axis. But that is not so in the case of your improper axis. The improper axis with n value equal to even gives similarly the n number of symmetry operations as that of your proper axis of rotation. So here we have generalized the statement that the presence of Cn symmetry element gives n distinct symmetry operations, namely this. And the presence of Sn symmetry element gives the n distinct symmetry operations, namely this, when n is even. Here n is odd or even, you get the same, but improper axis of rotation, when n is even, you get n number of symmetry operations. Then you may ask me, what if there are n is odd in the case of your improper axis? We will see it. Now before that, we will just look into this reflection point and we will try to identify the distinct operations generated by C5 and S6 axis. So you can just work it out in the notebook and you can look into the answers. And C5 is able to generate C5-1, C5-2, C5-3, C5-4 and C5-5, that is equal to E. So on the whole, here there should be an equal to sign, and on the whole there are 5 operations. Similarly, the S6 axis is able to generate S6-1, S6-2. S6-2 can be written as C6-2 into sigma squared. Sigma performed even times is E. So E into C6-2 is C6-2 again, and this can be simplified as C3-1. And similarly, S6-3 is generating C2-1, and S6-4 is generating C3-2, and S6-6 is equal to E. So this S6 symmetry element is able to generate again 6 different operations: 1, 2, 3, 4, 5 and 6. So it is able to generate S6, 5 and E. So here one small mistake is done. Here this should be 5. S6, 5 and E are the symmetry elements. Now, what happens when Sn, in the case of Sn, when n is odd? So when n is odd, there will be 2n distinct operations. Let us see it in the case of your S3. So S31 generates C31 into sigma 1. So that is S31. And S32 generates C32 into sigma 2. Sigma 2 is identity. So it is C32 into E is equal to C32. And S33 is C33 into sigma 3. So it is sigma. And S34 is C34 into sigma 4, where sigma 4 is E. So it is C31. S35 is equal to C35 into sigma 5. So C35 is nothing but C32, because C33 into C32. So C33 is identity, so it goes away. And the operation you get out of this is S32. And S36 is C36 into sigma 6. So C36 can be written as C33 into C33. So both are identity. So overall this is identity, and so it stops here. So this particular S3 axis is generating 6 elements, namely C31, C32, S31, S32, E and sigma. So when n is odd, we understand that there are 2n elements that is generated out of Sn axis. This is the very important thing that you have to note down, and we will finish this video soon, and we will once again meet in the next video, in which we will talk about how mathematics and chemistry go together to form chemical groups. Thank you.